This video is a detailed example problem of working an interaction diagram. My name is Tyler Lay, and I am cuckoo for concrete. We've been talking about interaction diagrams in previous videos. If you don't remember what they're all about, they are a diagram that we use to help design columns. Moment is on the x-axis, axial load is on the y-axis, this is compression, this is tension, and this is a failure plane. If you are above the failure plane, not good. If you are inside the failure plane, cha-ching! If you're right on the line, it's okay. It's okay. Now, we said this is actually a parabolic type shape. It's non-linear, kind of crazy, but we said, you know what? We can actually make this simpler. We can turn this into 4 points, point A, B, C, and D. Pure compression, balanced failure, pure moment, pure tension. Check my other video out if you want to learn more about that, but we are going to dive in deep today and actually work an example problem. So we're going to compute a 4-point interaction diagram, not just the 4 points, but also the fees as well, to draw the entire interaction diagram. Let's get started. This is what our cross section looks like. This side we're going to assume is in tension. This side we're going to assume is in compression. This steel over here is AS prime. That's the compression steel. There is 2 inches squared there. This is AS. This is 2 inches squared as well. That's 2 number 9 bars. We have a number 4 tie around the whole shoot and match. It's 12 inches wide. The B is 12. The total height is 20 inches. So we have 60 KSI steel, 4 KSI concrete. Here is the depth, the D to the tension steel, 17.5 inches. Here is the D to the compression steel, 2.5 inches. Now we're going to figure out point 1, pure A, pure compression. We're going to assume everything in our cross section is a strain of 0.003 and the steel is at yield. Now, why do we pick 0.003? Because that is like the strain limit that we usually assume for concrete. So if our strain is 0.003, our cross section is going to look like this. Everything's in compression. Everything. Compression, compression, compression. This steel is also in compression. This steel is also in compression, and it's also at yield. Now we're going to solve for 2 points, the axial load and the moment. Now the moment happens to be 0. 0, no moment for this point. Now this is what our axial load would look like. And I'm going to talk about it in pieces and work at it in pieces. This takes into account the concrete, all of that distributed load right there. This takes into account the steel here. This takes into account the steel here, and let's work it out bit by bit. This turns into 12 times 20. That is the B, that is the height. This is the area of steel at the top of the beam. This is the area of steel at kind of the bottom of the column, and this is 0.85 times F prime C, which is 4. Now we have to add in the area of steel that is in compression. That's 2 times 60, and this again is 2 times 60. And then if we add all of this together, our PN is equal to 1,042 kips. Man, that is a lot. That is a lot of load. Now, the C, in this case, that is the depth of the compression block, is the entire member. That C is 20 inches. We'll come back to this later on. Now we go to the balance point. The balance point, yeah, the balance point, that's at the tippy top of the beam. Look earlier in the video if you're not sure what I'm talking about. Now, we're going to look at a strain diagram that looks something like this. We're going to put this point right here in compression at 0.003. We're going to let it linearly vary from there. And that's going to end up giving us a stress diagram that looks something like this. This area is going to be in compression. We're going to have some steel that's in compression. Then we're going to have some steel that's also in tension. Now, to solve for this, I'm going to use my similar triangles. 0.003 divided by C equals 60 divided by 29,000 divided by D minus C. What I'm trying to do is figure out what that C value is. What is that value? And I'm going to assume, again, that some of these things are at yield. So let's check. So I get a C here of 10.36. That is the depth of the compression area, 10.36. And now I can go back in and use these similar triangles to solve for what my strain in my steel is at this magical point right here. So I take 0.003 times 10.36, that is the C, minus 2.5, that is that depth at the top. That gives me the distance here to that point. Divide that by 10.36, I get a strain of 2.27 times 10 to the minus 3. That is greater than 2.07. Where is that from? That is the yield strain of steel. Hey, that's right there. And why is that great? That means my assumption was right that I made previously. So now we can actually calculate what our P sub n is. This is what our axial load is on our cross section. Now we're going to add up this area, this load right here on the concrete, the beautiful concrete. 0.85 is my beta 1, and my C is going to be 10.36. My B is 12. And then again, I'm going to multiply by 0.85, and my F prime C is 4. Now I'm going to add to that this compression load, this compression load right here from the steel at the top that's in compression. That is going to be 2 times 60, and this is going to be minus 2 times 60. That is the steel at the bottom because it's actually going up. It's not going in the same direction as that, so it subtracts. Now, when I plug all of that in, I get 359 kips, and that is the point. That is the Y value at B. The Y value at B. Now let's find the X. Let's find the moment. So now I'm going to sum the moments about the neutral axis. That happens to be right here. So I'm going to take this load, multiply by its moment arm. I'm going to take this load, multiply by its moment arm. I'm going to take the resultant from the concrete and multiply it by its moment arm as well. Sum all the moments about that point. So first let's start out with this load down here. So I'm going to take ASFY times D minus C. That is going to be 2 times 60 times my D minus my C. That is going to be 20 minus 2.5 to help me find my D, minus 10.36 for my C. Now, that's taking care of that. Now, I'm going to split onto this. I'm going to take 2 times 60. 2 times 60. This is taking my compression steel, multiplying it towards its moment arm. 2 times 60. And then I have to multiply by 10.36 minus my D prime, which is 2.5. Now I'm going to move on to this point right here. This is beta 1C. So I'm going to add 0.85. That's my beta 1. 0.85 times my C here, which is 10.36 times 12 times 0.85 times 4. Beta 1C, B, 0.85 F prime C. I'm doing this to find my resultant from this point. My resultant from this compression load right here is found the resultant. That's the resultant. And then this is the moment arm for that. That is C minus beta 1C over 2. That is going to be C, which is 10.36 minus 0.85 times 10.36 all over 2. And if I multiply all of that, every bit of that, that is going to give me 2140 kip inches. This is the X value for point B. Now we move on to point C. You should have seen this before. This is pure moment. Oh, yes, I know pure moment. This is much easier. This is kind of like a doubly reinforced beam because we have steel in compression and steel in tension, but we're going to neglect the compression steel. So we get away with our good old favorite ASFY times D minus A over 2, and I can plug into this equation. Plug in here, and I get this value right here, 1923 kip inches. Now, if you don't want to neglect the compression steel, if you are a masochist, that's someone that likes pain, and you want to take into account the compression steel, you can, and you will get 1936 kip inches. That's a 0.6% difference. I think this is a pretty good assumption. See my other videos on doubly reinforced beams if you want to learn more about this. Now we go to point D, which is pure tension. Now you might say to yourself, whoa, 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 whoa. We have a moment. That's an X value. What is my Y value? Well, it's 0 because we have pure moment here. Pure moment. No axial load. Now we get to pure tension. So what's my moment going to be? My moment is going to be 0 because it's pure tension. Pure tension, hence the word pure. So I'm just going to take all the steel, all the area of steel, multiplied by yield. That gives me 240 kips. And ladies and gentlemen, I just solved for all these points. I just solved for point A, for point B, for point C, and for point D. All of them, they're all laid out, they're all ready to go. Now, let's just say someone out there wants to solve for a point over here. I'm not sure really why you would want to, other than you don't believe me that this isn't that big of a assumption to change this to a linear line instead of some kind of quadratic equation here. So let's just say we're going to use a C of 16 inches. That's going to give us somewhere here, because here we had a C of 20 inches, and here, if you go back to the problem we did for the balance point, we had a C of 10.36 inches. So we're going to pick somewhere in the middle. And this is actually how you do it in real life. If you wanted to solve an interaction diagram exactly, you would go back just the way I solved for point B, but you would assume a C and then go from there. So let's see that in action. So if we assume a C of 16 inches for this structure, that means this value right here will be 16 inches. We are forcing it to be 16 inches. And this is the strain diagram. This is 0.003, and we're going to now solve for the different bits and pieces of this. So let's solve for what our stress on our steel is. So let's use similar triangles right here and figure out what that is. That's 16 minus 2.5 divided by 16. That's C minus my D prime divided by C again, times 0.003 times epsilon s. I'm just solving for what my strain is at that point, and then multiplying that by the modulus of steel, and I get 73 ksi. That means 60 ksi. Good assumption. Good assumption. This can be 60 ksi. Now we're going to do the same thing for our tensile steel. We're going to solve for this distance here, right? Then we're going to multiply by 0.003, multiply by the modulus of steel, and we get 8.16. 8.16! That means this steel is only loaded to 8.16. That means it's nowhere close to yield when this thing fails. That means this is going to crush and break brittly and be dangerous. I've talked about this before in the other video. Everything above the noise is brittle, and below the nose is ductile. And that makes us feel a lot better. So now we go through the same math here, the same stuff I did before. This is where I multiply for and find out what my axial load would be. It would be 658 kips. And this is where I find my moment. I add all this together. I get 2798 kip inches where it falls. And woo-hoo-hoo, this is crazy that my steel only has 8.16 KSI of steel. And we've done this before. This happens in balanced reinforced situations, in situations where things fail in compression and not in tension. But if you might wondering what we just did, we solved for a point, another point on their interaction diagram. What we just did is we solved for a point with about 3,000 kip inches and about 658 axial load. So we found it to be about here. You might say, whoa, isn't that outside the diagram you had before? Sure it is. This diagram is a parabola. It's a parabola. We drew it and made it linear, right? If you're worried about this, you could solve for one point in between here and draw two linear lines, but I'm okay with one linear line, and I would suggest you use that as well. Now, the next step is to apply the phi factors. Those are the safety factors. I've gone over this already in a previous video. You should definitely go check that out if you don't know what this is. It's a fun video. I'm not gonna go through all these bits and pieces, but we've already talked about what happens in different points for different reasons on the interaction diagram. We also talked about something called the cap. That is the very, 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 very top of the interaction diagram. It goes up here. And we've also talked about something called 0.1 F prime C area gross. That is where we're going to assume this changeover point is in our phi diagrams, or somewhere that's a good estimate of the balance point. Let's jump right in. Now, I have summarized everything that we're going to do on this piece of paper. These are the steps to draw an interaction diagram. And we're going to draw one together, first in general, and then we're going to do detailed for the example problem we were just talking about. And we're going to solve and follow these points. First, you're going to find your cap. That goes at the very, very top. I showed that equation before. I've already given you here all the phis and something called the c's that we're going to use. Here comes up one of the c's right here. So if I'm using spirals, I have a phi 1 of 0.7 and a c of 0.85. If I'm having ties, a phi 1 of 0.65 and a c of 0.80. Previous videos have talked about these. Then we're going to find the upper boundary. What's that? Let's come over to the boundary here. This is what our diagram looks like. Everything above this point is what we're going to call upper. Everything below the x-axis is what we call lower. And everything in this middle here is what we call intermediate. We're going to find the upper boundary, find this point, multiply our point A by its phi factor, our point B by its phi factor. There'll be two of them. There'll be the axial load and the moment, and then we'll draw a line there. Then we'll find our lower bound down here. We'll find our point D prime by taking our axial load at D, multiplying by phi 2, and the moment at C, multiply that by phi 2, and then we will draw a line right here between those as well. Then we find our intermediate. And this is where it gets interesting. I'll explain it with words, then we'll see in action in pictures. So we're going to find this 0.1 f prime c area gross. It's going to go right there. Then we're going to draw this C prime line. I know that sounds strange. We're going to draw a line to here. It's going to be using our phi 1. Then we're going to draw our line for C prime. That is going to go from just here. That's going to use the phi factor 2.9. You'll see it in action in just a second, and you draw a line in between. Well, and then we're going to come back and erase part of that line. I'll explain it. It'll make more sense because we're about to do it right now. So here's our diagram, and we're going to go through these steps. We'll first start out, and we'll find our cap at the very top. That is that big long equation I showed you before, and what's going to make it, we're going to basically just draw a line up here, and that's going to be the cap. The cap. It's pretty straightforward. Plug into equations, not that big of a deal. Then we find our upper boundary up here. Now to find our upper boundary, we're going to take A1 prime, A times phi 1. A times phi 1. It's going to be a value that's going to go about here. And then we come around to our B prime, and we have two of them for our axial load and our moment. And what's this phi 1 going to be? Oh, well, it depends. If we have spirals or if we have ties, that will change what our phi 1 ends up being. But in our problem we've been having ties, so we're going to multiply this one by 0.65, so we come 0.65 over this way, and our moment actually comes down 0.65 as well. So it's going to be about here. And then we're going to extend a line between these two, and we have just drawn the upper boundary of our point. This is what we called A prime. This is what we call B prime. I hope you're following along with me. I'll leave these diagrams and some of these instructions in the notes for the video below. Now we come down and we do the exact same thing with the lower boundary. Right? We're going to take our D prime, multiply by its phi 2. What's phi 2 going to be? Oh, it's 0.9. And we're going to go to C and multiply it by phi 2, and then we're going to draw a line in between. Man, this sounds easy so far, right? So here's D prime, multiply it by 0.9. Here's C, we multiply it by 0.9, and we draw a line in between these two. Now what we've just done is this point is D prime, and this point right here is C prime. And now this is where the stuff in the middle, where things get a little bit more interesting, but it's not that hard. So the first thing we do is we draw our line at 0.1 f prime c a g. What is that line? That is an estimate of the balanced reinforcement line. And it's somewhere around here. That value is 0.1 f prime c a g. Now after we have that, we draw something called C double prime. C double prime. So we take our same point C, pure moment, we've multiplied, this one was 0.9 lower, this one is going to be 0.65 or 0.7 depending on what our phi 1 is, and we get a value here that's about here, that is C double prime. C double prime. Again, you would find that by taking C, multiplying it by whatever phi 1 is, and that would give you your C double prime. Now let's follow the directions here. We're going to draw a line between B prime and C double prime, and we're going to draw a line between C prime to the intersection between line C double prime, B prime, and 0.1 f prime c area gross. What? Let's see that in action. So we draw a line here from B prime to C double prime. Draw the line, draw a line, draw a line, draw a line right there. Line is drawn. And then where this line intersects 0.1 f prime c area gross, that point right there, we draw a line between here and here. Now, if we were using erasers, if erasable stuff, we would come back in and erase this line. this line would be out. And what we've just now drawn, what we've just done together is we have just drawn the interaction diagram. We have found point A, point B, point C, point D. We used our phi factors to find A prime, B prime, C prime. Actually, it goes here, doesn't it? It goes from here to here to here, and then down to D prime. Kind of nutso in here, right? That's how ACI decides to do it. So here's everything with numbers. We just did all this stuff theoretically. Now, here are the numbers. So these are the point A, B, C, and D that I solved for before with you. This is where I've multiplied out to find A prime, B prime. There's two places here. Why? Because B has a x-axis and a y-axis both. So B prime has both. Then we get to C prime. That brings it in. That C double prime, that's where we use the different phi factor. Then we get to D prime, just a little bit lower. And then we have our 0.1 F prime C area gross. And this is our cap. This is our cap at the top right here. Now, when we draw this entire diagram, all of this work, all of this pain has been for this. And this inner dashed line, this is what we use to design our structures. If we are outside this inner dashed line, no good. If we are inside the inner dashed line, good. So now what this means is that we can actually solve and see if this is a safe member or not by looking at the loads that are on it, by looking at the axial load and the moment that's on it, that's on the system, and see if it is safe or if it is not safe. Man, what a lot of work. Well, don't worry. There's something called a non-dimensional interaction diagram we're going to use coming up. It is crazy powerful. It's going to make this a lot easier. That is going to be the next video. I hope you dug this video. If you did, give me a thumbs up. Subscribe to my channel. Let other people know about this stuff I'm doing, because I'm doing it to try to help you and help others out there in the grand world of reinforced concrete. Take care, everybody. Bye.